We move on to the next section, and the next section has to do with what's called motional EMF, which is the generation of EMF by moving something through a magnetic field. And so the key formula here is that the EMF generated is equal to the magnetic field of the that the whatever it is moves through, the length of that object, and the velocity of its motion. Okay, so in problem number 18, we have a non-ferrous screwdriver is being used in a 2 Tesla magnetic field. What maximum EMF can be induced along its 12 centimeter length when it moves at 6 meters per second? And so in this case, you have a 2 Tesla field. The length is 12 centimeters or 0.212 meters, and the velocity is 6 meters per second. And so you do the math here, and you get 1.44 volts. Number 20, a 12 centimeter long rod in figure 2311 moves at 4 meters per second. What is the magnetic field if the voltage produced is 95 volts? This is number 18. Number 20 basically takes this formula and we're going to rearrange it so we can calculate field. And if we do that, then the field is going to equal to the EMF produced divided by the length times the velocity. In this case, it's 95 volts. The length, again, in this one was also 0.12, and the velocity now is 4. And if you do the math on this one, you get a field of 198. Number 31 moves into a different section. This is the section where we start talking about generators, and you'll remember in class last week I told you how generators basically work. And so the key formula that you need to know is that the EMF generated by a generator is equal to the number of turns. It's equal to the number of turns times the area of the loops in each turn times the magnetic field that it passes through times the rotational velocity that it is moving times the sine of the rotational velocity times time. Now you can again look in the book. If you're talking, now this is the general EMF. If you're looking at peak EMF, then you remove this correction factor for the various angles that the loop experiences, and this would be the maximum or peak EMF. And so it's going to be NAB times the rotational velocity. So in this, if you go back, it says, if you read this description, you'll remember I told you that we were going to come back to problem number 12. Problem number 12 was right up here, okay? We had this situation right here, and at the field produced was 0.425. And we need to know that to do this problem, okay? So B is equal to 0.425 Teslas. And the rest is given in that previous problem. So delta psi is equal to 1/4 turn times, and 1/4 turn in radians, remember there are 2 pi radians in a complete turn. And so that is not delta psi, delta theta, where theta represents the angular displacement. what I'm doing here is calculating the angular velocity which you need to do this problem. So theta in this case is not the way we've used it up here. Theta in this case represents the angular displacement in radians. And so if omega, which is the angular velocity, is going to equal to delta theta divided by delta t. And so it's going to be 1/4 times 2 pi radians divided by delta t, which is 4.17 times 10 to the minus 3. And so that's 376.7 radians per second. That's the angular velocity. So now we can calculate the peak, which is going to equal to this NAB omega, n being 500, area is pi times 0.5 squared, pi r squared, 25, excuse me, and b from the previous problem was 0.425, and then omega is 376.7 radians per second. And if you calculate all of this, the peak EMF is 1.57 times 10 to the 4th volts. 1.7 times 10 to the 4th volts. Part of that is because this is moving very fast. This many radians per second is flying, and it's a decent magnetic field. Number 33. Now, a lot of number 33 harkens back into the calculations that we did in the chapter on linear versus angular velocity. Okay. It says this problem refers to a bicycle generator considered in the previous problem. It is driven by a 1.6 centimeter diameter wheel that rolls on the outside rim of the tire. Now, if you've seen these generators, they basically lean up against the tire and the generator turns when the tire turns. So it says, A, what is the velocity of the bicycle if the generator's angular velocity is 1875 rads per second? So if omega is 1875 rads per second, it's asking what the linear velocity of the bicycle is. Well, linear velocity is equal to the radius times the angular velocity. And the radius, it's 1.6 centimeter diameter, so the radius is 8 times 10 to the minus 3 meters times 1875. And so if you do this, if you do the math here, you get 15 meters per second. And that's the linear velocity of the bicycle. The second question is, what is the peak EMF of the generator when the bicycle moves at 10 meters per second? Okay, so E0 is what we're after, okay? So E0 at one speed is equal to E0 at another speed, which is equal to the angular velocity over the angular velocity of the second. Since both of these, since E0 is equal to NAB omega, okay, if you put E0 prime and E0, everything else cancels out, and the only thing that's different is the angular velocity, okay? And that means that the new E0 is equal to the old E0 times the ratio of the angular velocities, which is equal to E0 times the ratios of the linear velocities. And the voltage in the previous was 18 volts when it was 15 meters per second. up here, it was 18 volts. And so now it's 10. So the new is 12 volts. C, if the sophisticated generator can generate its own magnetic field, what field strength will it need at 5 meters per second to produce a 9-volt maximum EMF? Okay, so if we rearrange, if we start out with E0 is equal to NAB omega, and we can rearrange that, and this will mean that B is equal to E0 over NA omega. But we're looking at velocity here. If we look at this and we put that in, if we substitute, if we rearrange this, omega is equal to V over R, okay? If we rearrange this. So if we put that in here, we get E0 times R over NAV, okay? Then we put the numbers in. We want a 9-volt output. R is 8 times 10 to the minus 3. N is 50. And A was 3 times 10 to the minus 4. And the new velocity is 5. So the needed field is 0.960 Tesla. Number 34 states, a car generator turns at 400 RPM when the engine's idling. Its 300-turn, 5 by 8 centimeter rectangular coil rotates in an adjustable magnetic field so it can produce sufficient voltage even at low RPMs. What is the field strength needed to produce 24 volts peak EMF? So omega is equal to 400 RPM, which if we multiply 2 pi radians for 1 revolution and 1 over 60 to change minutes to seconds, we get a omega of 41.9 radians per second. If E0 is equal to NAB omega, then B is equal to E0 over NAB, and this is going to equal 24, which is what we want to do. It was 300 turns, and the area is going to be the 5 centimeters times 8 centimeters, or an area of 4.00 times 10 to the minus 3 meters squared, times B, which times omega, I'm sorry. Yeah, I got the wrong number there. This should be B, or omega, which is 41.9. And we get an answer of 0.477 Tesla for the magnet. We're going to do the one problem on back EMF, which is number 40. And back EMF is essentially the idea that engines can produce their own EMF, which resists the EMF that you're trying to produce. A motor operating on 240 volts electricity has 180 volt back EMF at the operating speed and draws 12 amps. What is its resistance? Okay, so the resistance is equal to the net voltage divided by the amperage. And the net voltage is 240 minus 180 divided by 12. which is 5 ohms. What current does it draw when it's first started? When it's first started, there is no back EMF. An engine has to get started for a back EMF to be generated. And so you put in the original voltage because there's no back EMF until the engine gets going. And then that divided by the resistance is going to give you a initial current of 48 amps, which is why in some situations when a car or some engine is started, it can blow a fuse that it would not normally blow.